When we write a number like 123, we're actually writing a sum. 1 times 100, 10 squared, plus 2 times 10, plus 3 times 1. And in general, a base p number is a sum of the form a0 plus a1p plus a2p squared plus a3p cubed and so on, where the ai's are some number between 0 up to but not quite equal to p. Suppose we're trying to find a solution. If we write x as a base p number, we can find x mod p to the power k for increasing powers of p. So x is congruent to a0 mod p because all the higher order terms drop out. X is congruent to a0 plus a1p mod p squared. X is congruent to a0 plus a1p plus a2p squared mod p cubed, and so on. This suggests we might be able to solve for x digit by digit. For example, let's try to solve x cubed equals this horrible number. Suppose we work base 10 because, well, that's how we write numbers. We note that 1000 cubed is greater than the number, so we know the solution only has 3 digits. So let x be a0 plus a1 times 10 plus a2 times 10 squared. If x cubed equals horrible number, then x cubed is congruent to 3 mod 10. But if x is, then x cubed will be congruent to a0 cubed. So we can use trial and error to find a0, and note that because a0 has to be between 0 and 10, we don't have to try too many things. So we want to solve a0 cubed congruent to 3. By trial and error, we find so a0 is 7. And note that's the ones digit of our actual root. So we know that x is 7 plus a1 times 10 plus a2 times 10 squared. Now if we work mod 10 squared, we want to solve, where the a2 10 squared term is going to drop out. Again, by trial and error, we find, and so a1 is 2. And so now we know that x is 7 plus 2 times 10 plus something times 10 squared. So if we work mod 10 cubed, we want to solve 27 plus a2 10 squared cubed congruent to 783. Again, by trial and error, we find, and so a2 equals 3, and so x is 327, and we verify that 327 cubed is in fact our number. While this seems to be a workable approach to finding roots, we can't actually use it unless there is a whole number solution. For example, if we tried to solve x squared equals 157, we'd let x be some 2-digit number and get a0 squared congruent to 7 mod 10, but this has no solution. However, if we're trying to solve a congruence, we can use this approach with 2 important changes. First, because powers are continuous functions, we could place an upper bound on the value of the root, so we knew that the solution only had 2 digits. But if we actually start with the congruence mod n, the actual solution could be any value up to n. So we need to continue until we found all digits of the solution. Second, we're given the modulus and don't get to choose it. So for example, let's try to solve x cubed congruent to 232 mod 7 to the 5th. Since we're working mod 7 to the 5th, the solutions could be as large as 7 to the 5th. And since we're working mod 7 to the 5th, then we'll assume that the solution is some number written base 7, which is going to be where the AIs are to be determined. Now suppose x cubed solves this congruence. Then 7 to the 5th divides the difference. But since 7 is prime, this means 7 divides the difference. And so this becomes a congruence. Again, if we're working mod 7 and we assume that x is some number base 7, then x will be congruent to just that first digit. So our congruence becomes a0 cubed, and we can reduce that to 32 as well. And so this gives us a much simpler congruence, which we can solve by trial and error. And again, since we're working mod 7, we only have to try numbers up to 7. And we find that a0 is 1, which will be the first digit of our solution. So we know that x is 1 plus something. Again, since 7 to the 5th is going to divide the difference, then 7 squared will divide the difference. So x cubed is congruent to 232 mod 7 squared. And as before, we know what x is. Reducing it mod 7 squared will eliminate the higher order terms. And so our congruence becomes. And while it's not obvious, we actually only need to try values up to 7, because remember the AIs represent the digits of a base 7 number. And so we can try this by trial and error, and we find so A1 is equal to 4, and that's the next digit of our solution. So we know that x looks like working mod 7 cubed eliminates the last couple of terms, and so our congruence becomes which we can solve as giving us our next digit. So again, x looks like working mod 7 to the 4th eliminates that last term, and so we get and again, by trial and error, we find that next digit is 0. So x will be working mod 7 to the 5th gives us, and we find a4 is 0 as a solution, and so we have x. And we verify that 323 cubed is in fact congruent to 232 mod 7 to the 5th. Now this method will work to find a solution, but any method relying on trial and error always leads to the question, is there a better way? Maybe, but for that we'll have to develop more math.